Hi, my name's Andrew K. Fletcher, and I want to tell you a little bit about my discovery back in 1994 when I worked out how trees and plants circulate sap. And one of the first experiments I did was with a spirit level, not the spirit level we're all familiar with, but an old-fashioned spirit level made from a single length of tubing. And the tubing is filled with water, and we've chosen warm water so that it straightens out the soft tube. So we'll siphon in some water, stop it filling up any further, and so long as there's no bubbles in and the density is always the same, just make sure that all the bubbles are coming out. There's a few in there, but what this enables us to do is to have a spirit level that gives us the same level in both sides of the tube. So if I was building a wall, then I'd set the height of the tube to match the height of the wall I wanted, or the height of the water level, and that would give me exactly the same level at the other end of the wall. So irrespective of the length of the tube, so long as the liquid density is the same and there's no air locked in the tube, we'll always get the same level. And it doesn't matter where you put that tube or how long that tube is, as long as there's no air locks in and the liquid is the same density, then those levels will remain the same. And the density is the key in inclined bed therapy. Change that density and you change the power source. But my discovery went a little bit further. Because I said, what if the density was different in both sides of the tube? And for this we've coloured some salt solution with food colouring. And now let's introduce some coloured water to see what difference, coloured salt solution is, to see what difference that makes to the level. Now you can see that we have a driving force. And I've left this experiment standing for almost a week, and that density difference and that level difference remains in place. So that's a problem for diffusion as well, because there's no semi-permeable membrane at the bottom of this tube. It's just where one fluid meets the other fluid. So here we can see the level difference. And if we were building a wall and we accidentally got some denser liquid in one side of the tube, the wall wouldn't be straight. But this has more implications, because what we're seeing here is a driving force. So if a plant, for example, was able to deposit denser solution in one side of a loop of tubing, i.e. inside the phloem vessels, then that would give us an increased height in the xylem vessels, and that gives us the impetus for plants and trees to grow taller. So they actually benefit from growing taller, making use of the density differences between the sap in the xylem and the sap in the phloem. So the liquid has flowed all the way down to the bottom, and at the bottom where the dense solution meets the water solution, you would expect it to dissipate, but I've left this for a week, and There's not much change in the level at the top of the tube, and there's not much diffusion going on at the bottom of the tube where the saline solution meets the clear water. So this is a very interesting discovery, in that it gives us a clearer picture of how aquifers work in coastal regions, where fresh water can raise the water level way above the sea level, and that stops contamination. The next experiment is with a closed loop of tubing, and this closed loop of tubing was used to determine the angle for inclined bed therapy. And what we aim to show is that circulation with a density difference can occur inside a closed loop of tubing. Our system is semi-closed, so this again was a good experiment for both trees and for both human physiology. A little bit trickier to set up. We fill the loop of tubing up with water already, but what we're trying to do now is introduce a little bit of coloured salt solution to one end of the loop of tubing. And to do this, we need to introduce some salt solution and then close it up without getting any bubbles inside the tube. So again, we need to just repeat this by lowering the levels, and then cap it off with a finger, and then both tubes are then placed under water. And one tube we need to lift up. My dog's complaining about being ignored. And then we'll introduce some salt solution to the tube, and carefully, like I say, it's a little bit fiddly. I could do with probably getting a larger bowl to work with, but so long as we don't Ruby, be quiet. Now we have our coloured salt solution, which is locked up in one side of the closed loop of tubing, and when we actually elevate the tube and release the salt solution, we'll see the circulation occurring down the loop of tubing. So before we start, we have a closed loop of tubing filled with water, and we've added some coloured salt solution to represent the arterial flow in the body, and also the phloem vessel and the phloem flow inside the tree. And it's, at the moment, there's no migration because we have a loop where we fastened or secured the tube to the top of the ceiling, and the tube is closed all the way down. So now we'll release some of the salt solution. And we can see the flow in the closed loop of tubing. Going all the way down. But for this to happen, the fluid or the liquid in the other side of the loop of tubing has to go back up. And we've shown this by adding two different coloured dyes, one for the downflow, which is a blood coloured liquid, and in the past we've done this with a return flow in blue to represent the venous return in human physiology. In the case of incline bed therapy, this same closed loop of tubing was spread across the length of a bed from the head end to the foot end, and when the bed was horizontal, obviously you just had normal diffusion, which was very slow. When the bed was raised to 4-inch raise, then the salt solution ran down the bottom edge of one side of the tubing, and the clear water ran up the same side of the tubing, so we had a two-directional flow in one length of tubing, or one side of the loop. When the bed was raised to 5 inches, then we had an overall circulation of the tube. In other words, we had a downflow, which represented the arterial blood, and we had a return flow, which represented the venous blood in the opposite side. So the whole loop was circulating, and we did it again with soft wall vessels. And what we've shown is that this denser blood, or denser liquid in one side of the loop of tubing, was capable of inflating the one side and deflating the other side. Now this is very important because it also explains why people sleeping on an inclined bed have noticed varicose veins going flat over 4 weeks without surgery. And the reason this has occurred is because when we've increased the flow in the arteries, we've actually increased the pressure slightly in the arterial side, and the same goes for the sap in the tree. We've increased the pressure in the phloem side, but we've decreased the pressure and applied tension to the blood and the xylem sap in the tree. So the venous return is actually under a tension and a lowered pressure. Now that explains why the veins are being pulled in, and in fact if we take that a stage further, then what we're looking at is when we're lying on a flat bed and we're relying totally on the heart to drive the blood around the body, then the heart is a pump, and we know arteries are capable of withstanding the pressure, but veins are not. So because it's a pump and it's not getting any assistance from the density check differences in the blood, and then what we're seeing is that the pumping action of the heart will actually increase the pressure in the veins, causing the soft wall veins to bulge out. My bed is raised 58 centimetres at the head end. At the foot end, my incline bed is raised 40 centimetres. And I've made a video showing how I achieve this. But the point we're going to show now is how that incline can influence the circulation when there is a density difference between the blood flowing in the arteries and the blood flowing in the veins, which will always be the case, because when we evaporate water with every breath we take, that water is supplied by the blood that supplies the lungs. So through the capillaries we evaporate water molecules, therefore the blood exiting the lungs is always denser than the blood entering the lungs. This denser blood then goes through the heart and is injected back into the main arteries, and it's very akin to placing a pinch of salt at the top of the arterial tree. And if we're on an incline we can make use of it. If we're sleeping on a flat bed we can't. If we're sleeping on a flat bed we rely entirely on the heart to get us through the night. Now what we've done is we've stretched our closed loop of tubing down the length of an incline bed, and just over the edge of the mattress we have a loop which contains our coloured salt solution. So what we're going to do now is just release this. I've used a slightly wider or larger bore tubing than I have done in the past. But we can see there is circulation taking place in that closed loop of tubing, representing the downflow in the arteries. Now this will occur whether the heart beats or not. This is primary circulation. Here we have a simple experiment designed to show how solutes change pressures in soft wall tubings to represent the venous return. We have two vessels linked together with tubes placed at equal levels at the bottom of the vessels. We've added a small yellow dye, small amount of yellow food colouring to the return flow, and we're going to introduce some saline solution coloured red via a T-junction at the top of this experiment. The vessels will now be lowered to ground floor. As we can see, there is no flow. Now if we introduce some salt solution at the top, we can start to see the yellow return flow drawing water from one vessel, while at the same time the salt solution is flowing down, causing the other vessel to overflow. Could we have a top up there, please? So we have a return flow in yellow, which is being drawn up, and a downflow in red. But if we examine closely, we can see that the salt solution has caused the one side of the tube to neck in the return flow side, which is designed to show how solutes could cause a stenosis in the venous return. Just going to introduce some more salt solution now. Again we see the downward flow and the return flow in yellow. Again, the closing of the tube indicates the tension applied by the falling solutes. Just going to introduce some more salt solution so we can see it again. And the tension is applied to the whole length of tube. Again, more salt solution. And the yellow solution is now being drawn back down, so we've completed the circuit.